Okay, so welcome back to the second part of our lecture on unsupervised learning techniques. In this part of the lecture, we're going to talk about a very important concept called principal component analysis. Principal component analysis, or PCA, is often used before supervised machine learning algorithms are implemented. And the idea is to extract out the features that mean the most in the data, right? Because a lot of, if you have like, suppose you have like 15 features, right? And you're trying to train a machine learning model on this, like the more features you have, like the slower it might run, right? Or again, like because the data becomes very sparse in high dimensional space, as I mentioned, like this semester, or like earlier in the semester, we want to like condense that all those features down to the important ones, the features that have the most variance among them, right? So like if all of the classes on one dimension are like just together, that doesn't really do anything for us, right? We want to look at the dimensions where the classes are separated a lot. We want it to be easier for our machine learning models to find separating hyperplanes. Okay? And the way that we do that is with principal component analysis, which is essentially looking at the singular value decomposition of the feature matrix. So the singular value decomposition you might not know of, but it's very important in like applied linear algebra. But if you know about the eigenvalue decomposition, then the singular value decomposition of a matrix is equivalent to the eigenvalue decomposition of A times A transpose. So they're related. And if you know what like eigenvalues do, they stretch. Like you can think of like a matrix as like a linear operator, right? And you can like multiply things by a matrix, right? The eigenvalues are going to somehow like stretch in directions. And the singular value decomposition is like, there's a really nice geometric interpretation that I'll provide like a link for like an article on in the YouTube video. Okay. All right, so as we've done quite often, we're going to look at the iris data set again, and we're going to consider every single feature, right? All four of them. But recall, like in the past, we've for visual purposes, we've like just picking two at a time. But how do we know that we were picking the best two features? We were just kind of doing it arbitrary. With SVD in the PCA, we can find out which dimensions are the most important, which two, right? So in order to do this, we start with our feature vector, or feature matrix, and we're going to first center the data around 0. So along each row, we're going to take like the average and then subtract the average. This will center the data. And then this is kind of optional. I don't do it below, but when we implement PCA with scikit-learn, it will do it. Divide by the standard deviation. Okay, so doing this will create new values in our feature matrix for each entry, right? And we'll denote that by the matrix A, the resulting matrix that you get. This centered and scaled matrix. Right, and scaling is important because sometimes you can have features that are like, if you have like a person's height, but then you also have like they're like, I don't know, like some measurement of like their finger or something, like there can be like lots of skewing in it, right? So like centering only is not enough when you have data like that. You need to also scale it so that they're all kind of with each other. Okay, so once you do that, we compute the covariance or correlation matrix. So covariance, it's just this, like if you do just the mean, it's covariance. If you do divide by standard deviation, it's correlation. But as you'll see below, just by centering it, because the data is already kind of like in the same range, I was able to project onto, well, I haven't even talked about projection yet. I need to get there first. But yeah, so this is the matrix S. So you make your scaled centered matrix A times A transpose, divide that by n minus 1 if you have n entries of data. Okay, so we have, I have a description here. So just go ahead and read that later. I want to get to this. This is like the thing right here. So this is a matrix factorization here. Right? So we have U, which is, so we have like, I don't like the description sometimes of relating it to the eigenvalue decomposition, but maybe I should relate it because I don't know if standard linear algebra courses really talk about the SVD, but I know they talk about eigenvalues. So basically, the middle matrix here is a diagonal matrix where the diagonal entries are denoted by sigma I squared. These are called the singular values, and they're listed in decreasing order. So like the highest singular value is in the 1, 1 entry, the next highest is in the 2, 2 entry, and it's just going down, right? And these singular values are basically telling us how much this matrix will like stretch vectors when multiplied by. And then here in this V here, actually, I'm going to make a little video for you guys. I think it's really important that you understand like why this is possible, because not every matrix has an eigenvalue decomposition. That's like many don't, right? But every matrix has a singular value decomposition. That's what's so special about it. That's one of the special things about it. But in any case, the vectors inside of V transpose are called the singular vectors. Like, so each column in there is a singular vector. And these vectors, well, let's go ahead and like calculate it and then we can talk about it. So here I center my matrix. So X is like the sepal length, sepal width, petal length, petal width. Right? So I center it. I don't scale it in this case. I don't need to. And then I use NumPy's linear algebra module, the SVD, to calculate the SVD of A. And it's important to put full matrices equal to false here. And you get U, sigma, and then V transpose. So let's look at their shapes. Running that. So U is 150 rows by 4 columns. The sigma diagonal matrix, because you don't need to store all those zeros. Like if you know it's a diagonal matrix, there's no need to store all those zeros. It's just a vector with the singular values in it. And then VT is 4 by 4, and these are the singular vectors. Okay. So we can verify that this is indeed the factorization of A. So I say sigma matrix is equal to the np dot diag of the values in sigma. So it just makes a diagonal matrix with those values. And then np dot all close is a way of comparing this matrix here to this product, this matrix. And it's because some information is lost in the factorization, like up to like floating point problems, right? But we can still verify true. So A is indeed equal to this, U times sigma times VT. So it's a proper matrix factorization with maybe a little bit of noise introduced when factoring. Okay. So in my notes here, I say eigenvalues. I really should say singular values, but again, the singular values are the eigenvalues of A times A transpose. Okay, that's the same thing. They mean the same thing. Okay. The first principal component is the first vector in V. It's an eigenvector or singular vector, as I was saying earlier. I'm going to rewrite this whole thing for singular vectors and not eigenvectors. The second is the second principal component. The entries of each of these principal components, of the things inside of V, right? These are called the loading scores. That's like more of a data sciencey thing than like a math thing for me. So I just wanted to mention it because they mean the same thing. But they do tell us about the linear combinations of the features and how like how well they fit together. Like if you're looking at like variance between things and they're all on top of each other, then like you'll know it by looking at these things, as we're about to see. Okay, other kind of things that you should read after you watch this video. Because here, this is the important stuff. So here's PC1, PC2, PC3, PC4. Recall that these are 4x4, like V transpose is a 4x4 matrix, right? And then here are the first two singular vectors, 0 and 1 singular vectors. Recall that this is non-inclusive on the right-hand side. So it's 0 and 1 columns from that matrix. And then if I multiply that with A, think about, so A, like what are the dimensions of A? A is 150 by 4, right? And so there's 4 columns. There's 4 rows here. So it's like, you understand what the dimensions of the output is going to be, right? It should be what? Well, let's just check. X2D. It's that, right? There's 2 columns and 4 rows, and A is 150 by 4. The dimensions match up, you should get 150 by 2. Okay. So maybe we should like look at it. What is it like? What does it even look like? It's this. It doesn't look very descriptive of anything, right? Like we started with the iris data set, right? We know what those values look like more or less by now, hopefully. And this doesn't look like anything like that, right? But you have to remember that we have what? We've centered the data first, right? So, okay, let's see what happens when we plot this data. So here's X2D, 0 column, 1 column, colors, it's okay. That looks like the data. That looks like the iris data set, right? Like some combination of them, right? In fact, it is. It is a combination of them. And if we were to learn to train a classification algorithm on this, we would be able to classify the iris data set as well, right? We could take the data that we read in, do this data manipulation to it, then train an algorithm on that data. And then any new data that we take in, right, we just do the same thing. We compress it in a sense, or project it, that's what I should say, project onto the principal components, and then make a classification prediction on it based off of that. So notice that like we took in the 4-dimensional data and now it's 2-dimensional. And the classes are the same, right? Like it's like versicolor, setosa, versicolor, virginica. And on these axes, that's where there's the most variance in the data. Like look at how like the setosa in the y-axis, like look how far stretched it is like that, right? It's like really stretched. And then look at on the x-axis, like the range of values between the data points. Like on the x-axis, that's the most variance in the data, right? It's like, so while like you're looking at it, what happens if I do this? What about if I say, I guess I could just do, I'm going to change this now, 2 to the end. So what did I just compute here? So this is now the last 2 singular vectors, the last 2. Those do not describe the variance of the data as well, right? Like I mentioned earlier that it's in like decreasing order, right? The first singular value is like the magnitude of scaling and it's the largest, right? And that's corresponding with the first singular vector. Next singular value, next amount of stretching, and then also the corresponding singular vector. And it's just getting smaller and smaller. So the last two, right, should have the least amount of stretching in the data. So here's what it looked like before with the first two singular vectors. And then I'm about to do it with the last two. See that? There's barely any like separation in the data. Look at the x and y, like the x values here, negative 0.8 to 0.6. They're like on top of each other, right? But if we go back up here and we look at the first two singular vectors, like that, come back down here. So this is the last two singular vectors. Look at the range here. Look at the range here. It's pretty small. Now look at the range and look at the spread in data. And it's because of that like stretching that I was mentioning, right? Like that stretching corresponds to like variance in the data. Okay. Luckily for us, we don't have to do this by hand every time. By the way, you might want to mute your mic. I think I'm picking up. Yeah, there it goes. So sklearn has PCA built in, principal component analysis. So this will calculate the SVD for us, and it will scale it for us and center it for us. It does all of that for us. We don't have to do anything. So, and also pre-processing here. So this will do the scaling for us. Sorry, I misspoke. But PCA does center it for us by default. So here's scaled x. So I take the x and I scale it, calculate. So I instantiate the PCA class. And then as you know, in sklearn, there's the fit method. So it's not like, there's no y values to pass in here. This is just fitting the PCA method to this scaled x. And PCA, this variable, is indeed a class, it's an object, right? So objects have the methods like this fit method, but then they also have attributes. And one of the attributes is the explained variance ratio. Okay, so I'm going to print out the explained variance ratio after it's been scaled. And then here, I'm just going to round and make those values look like percentages, because that's how it's easier for me to look at them that way. And I'm rounding to 2 decimal places. All right, so what does this do? Okay. So here are like the percentages in the like explained variance, right? Look at like 72% of the variance in the data comes from that component. Basically 23% of the explained variance comes from that component. Barely anything comes from this component at all. In fact, so 72, so over 90% is described by the first two components. And if that's the case, if you have over 90% of explained variance in the first two components, then use those two components to train on. Okay. So then we can like visualize this, like these explained variance ratios with what's called the Scree Plot. It's basically a bar chart. That's all it is. It's just data scientists like to call it that. So I run that. It's just a bar chart of those variances, explained variance ratios. PC1, basically everything, a sizable chunk from PC2, and then it just falls off. Like those measurements don't mean anything in separating the data. So like imagine you had like a bunch of features, right? You'd want to do this to figure out which components to learn on. What are the features that are most important? Okay, and we can like, oh, this will give us a nice visualization. So I just get the feature names from the iris set, and then I make a data frame. So these are the components here. So in this case, like PC1 is equal to 0.52 times the sepal length plus 0.37 times sepal width minus 0.71 times petal length. So PC1 is a linear, like each of these are linear combinations of these values here. And that is high, right? They're like all like pretty much high here on petal width here. Okay, so let's now look at the entire iris data set in terms of the principal components. Right, like we're transforming the data. I can't, like, maybe I didn't emphasize this enough, and I will in like a short video I want to make for you guys in the PCA, right, on SVD. But we're basically taking the data and mapping it to a different coordinate system. And this mapping is preserving the labels like as they should be, but it's mapping to low dimensional space from high dimensional space. And so PC1, PC2, these are like our new axis values, right? And we're only really concerned about PC1 and PC2 because they take up most of the explained variance in the data. So I'm going to add on to this projected, or no, I make a new data frame here. It's my principal component data frame, and then I concatenate that with the iris species so I can have like the labels. So the labels are still there. We're just on a new axis now. I don't need this anymore. All right, so what am I doing here? So targets and colors, you should know what that is. Set my fig size for target and color and zip of that. Temp df is like where species is equal to target. So like Setosa, first light color, so forth and so on. And then I scatter the data values on the first principal component and the second principal component. And then I give it the color. So red, magenta, light sweet green. And then I just plot. So on PC2 and PC1, like this is the data. It's the same exact data. It looks like the iris data set. We've seen that plot before. But among all the possible combinations of features, this is the one with the most variance in the X and Y value, like possible out of all the data. And just to like illustrate this even more, like what if I did PC2 versus PC3? Let's see what happens to the data. It's all over, it's like more on it on itself, right? If I did PC3 and PC4, it's like even more jumbled on each other. But on PC1 and 2, it's like that. Like, and that's because of those explained variance ratios. It's like how much of like this component is the data spread on, right? So to illustrate how we can use this on like higher dimensional data, I'm going to load this breast cancer data set from scikit-learn. Okay, I always load these things as data frames. So here are the keys of this. So this returns a dictionary, but each object in it is now a data frame. Okay. So here are the keys. So the features of this data set are these measurements. And then the target names are malignant and benign. Okay, so then I grab my data frame out of there. There it is. Look at all those features. How many are there actually? Well, oh, it's inside of that. It needs to be outside. There. There's 30 features. So each feature vector is a 30 entry column vector. Right? That's a lot, right? Like out of all of those 30, which would you choose to use in a machine learning algorithm, right? All right, so we're going to pre-process and scale our data. So we have scaled X now. Okay. So the features, we make an X value, we scale it, that's what it is right here. PCA fit. Let's look at these explained variance ratios. Even trying to make them look like fractions, it's hard to tell what's going on, right? Like what is that number there? What is that number there? What is that number there? So that's where looking at one of these bar charts will help. So there are 30 principal components because there's 30 features. And yeah, let's look at this plot. So you can see a lot of it is taken up by principal component 1, 2, and 3. Right? So let's see. All right, just like before, like each row now is one of the features, and then we have these principal components on each of those features. There's 30 of them. So we can make a new data frame. So PCA data, the labels that we have. There. So this is how many rows were in the original data set. Those are each like instances of patients, right? So now we can just look at the first two principal components. There it is. So out of all of, like, this is going to look exactly like, if we like reverse this and look at the features that correspond to these principal components, right? If we like went through all the features and like was just plotting and plotting, one of the plots would look exactly like this. And it would take you a long time to find because there's 30 features, right? But these two components describe, I didn't look at the actual numerical measurement, I should have, but most of the explained variance in the data. So you would use these principal components to try to classify malignant versus benign. So then you have like a pipeline. You have a pipeline like you train on this data, right? So if you get new data, you have to transform it. You have to scale it and do all those things. But once it's scaled, you feed in and then you get a prediction. Question?
How do we know what the
So you can find out exactly what those are. Let's see. Here. Oh no, why did I do that? It's PCA. Okay. So there should be a method I'm looking for. Where is it? Here. So by calling inverse transform, you can take the matrix that you have and take it back to the original space. Like this is one thing that's nice about sklearn. I just saw a method that I hadn't noticed before. I will come back to this actually. I don't want to go down the rabbit hole of looking up that documentation right now. But okay, so this is like just a dimensionality reduction technique. And I want to make to address like the question I just got about going like figuring out which features are there. It's actually very simple, but I want to make a short video on SPD first and like explain it in there. But for now, just know that if you have high dimensional data, you can use this technique to kind of find the important things, right? Or the things that have the most variance, right? Like if you're trying to like classify things, you want them to be spread out, right? And a lot of times they won't be, right? Like if I were to like look at PC, I don't know, 2 and PC 3, like on each other. There you'd have, and if you were looking at the original data set, one of the plots would look exactly like that. And you would be like, I can't classify this. But because of principal component analysis, we can. Okay. I would like to mention one more thing just before we finish for the day. This factorization, this SPD, can be used in data compression as well. So like think about like, so coming back up here to this, like, where was it? It is right, well, it's a long notebook, okay. here, right? So what did we do here? Like we have like this x2d, it's like kind of, it contains the information that's important, right? So this factorization, you take something that's like a big square matrix, like an image, right? You can factor it into matrix times diagonal matrix times singular vector matrix. Well, immediately when you do that, you can store the diagonal as just like a column vector, right? So you eliminate a lot of entries of storage, right? And maybe, actually, let me see something real fast. I was not planning on talking about this, but I feel like I would be giving you a I don't know, I just feel like I need to do this. Just show you something real fast. This is a very old notebook that I have. Just because I want to emphasize that the SVD is like really cool. So here's an image. So this is written in Julia, by the way. And this is like not even Julia 1.0. This is a while ago, before 1.0 came out. All right, so here's an SVD. There's like, and it's like, there's a lot of pixels, right? Like how many pixels are in here? So 512 by 512, right? So here's the sigma in the SVD decomposition. Look what happens when I take the first two columns of U times the first two singular values times the first two singular rows, because that's like V transpose right there. So looking at the rows, this is what I get when I view that matrix. So the original image is 512 by 512. And we're eliminating 510 columns here, 510 columns here, right? So like, but we get something out, right? What if we look at the first 10 columns, first 10 singular values, first 10 rows here? It's almost that image again. First 20, first 30, 40, 50, first 100. That's basically it. So that 512 by 512 could be something like 100 by 100. It can be stored in such a way. Right? And that's because, again, as I was like kind of hinting at, like the singular values are describing like the most information of the matrix. And you think of like data inside of a matrix, there's spread in it, right? Where is most of the spread happening? It's happening with respect to the highest singular values and the singular vectors. Yeah, so that's just important to note, I suppose. And I'm going to provide you a lot of resources if you want to go down that rabbit hole of learning more about this. Okay, so I guess that will be it for today. I'm going to go ahead and stop the recording here.